conduit manifold to commingle all the fluid from the fluid. The manifold is fitted with lifting points for rigging a vessel. And the protocol is different, like the same goes with the previous one. We transported the manifold on the LTP, whereby it will become way to what has to be trained around 400. Okay. So, flight over the cargo side central, then continue reach the weight of the manifold. In fact, both involve slicing with the sample, not for that compared to the luggage of the next area. So again, during the lowering, the speed of lowering, because structured, they are designed for a certain speed of lowering. That's the next thing. We do not quite. And you will see there's a stabbing guide. So this stabbing guide, staggered with the other stabbing guide at the other component, will allow one guide to stab one corner of the cone. And once the cone captures that one guide, then the other corner will then be captured. That's the favorite. Once both corners are captured, manifold is then lowered down into the and then the same operation goes more vectors. The rigging, the recover the beam. There's no suction operation involved or anything. One to that is the ending. To perform as-built survey, as-lab survey, monitor the condition, we know that condition, everything is okay, then it's done. The next one is installation of the Christmas tree. So Christmas tree are attached to the wellhead, provides the flow of the flow from the wellhead to the flow line. It also acts as an except for well intervention operation. The Christmas tree at the top is equipped with a lifting cap to allow us to attach everything. You can see right now this is the preview method. This is the tree subsea, and this is how we installed the tree offshore, where this shows the ROV screen and this shows the survey. Now, I'm going to show you how we display method of installation other than video. You don't always have the luxury to have video animation every time you want to install something. So we usually do what we call an installation storyboard. So it gives a step-by-step illustration on how we perform installation. So for example, in this Christmas tree, it shows that vessel will be positioned close at a safe distance from the wellhead to avoid damage if there's any drop object. We'll connect up the rigging, we'll pick up overboard the Christmas tree and then lower down. So you can see from this storyboard, well enough without an animation video. And then lower down the Christmas tree, go to the wellhead, put on the wellhead, block the Christmas tree, and then operation then. So the next structure to be installed is a flat or ILP magnet. To support flat or ILP also prevent it from sinking from onto the seabed. They also act as a target block for the pipeline operation. So this is the flat. So there are two types of flat, the one with integrated magnet and the one without. With and one without. The flat is usually located at the end of the pipeline. So it's usually welded to the pipeline and it's usually installed by the pipeline. It sits on top of the magnet and serves as a base to connect the jumpers to the manifold. This is the jumper. So in this one, you can see this is a rigid jumper. It's a 2D rigid jumper. And this is showing the jumpers installed on the bed. It easily connects between the flow line, the flat, and manifold. For the manifold, deep for the structure. So yeah, here is the vertical connector, but they also have horizontal connectors. But there are also flexible jumpers. And then umbilical installation. The structure involved is the UTA, umbilical termination assembly. So this is like a flat, but flat is for flow line. UTA is for umbilical. So it's located at the end of the umbilical. And if you see, this is the UTA. This end will be connected to umbilical, and this guide will tap onto this UTA magnet and sits on it. This UTA will then connect it to the same distribution unit via. So this is the key distribution unit. So this is a key, it's like manifold, but for umbilical. So it distributes fluids like chemicals, and then electrical signal for power, electrical signal for sensor, and electrical for power. It distribute from the umbilical manifold or much for umbilical. No, those are small structures that are installed. Involved for subsea installation. They use documents for the cloud plan, etc. The constructability study. When you say constructability, we want to see how this offshore are there. So we need to see what is the weight of all of the trucks, because it will determine the pressure of the what is what then, because it will determine the vessel train maximum water depth. It will also determine the maximum ROV working depth. When we specify these vessel requirement, we need to know what are the structure, weight, water depth, what is the size of the structure, and other installation spread. This will determine the minimum deck space of the vessel. Sometimes when you install Christmas tree, not only the Christmas tree that you as that is the determining factor, but there are installation spread that involved within the design. Solving it, you have to have a tree possible for you make sure that the deck space of the vessel is enough time for the Christmas tree. Not only the Christmas tree, you will also need to see what is the structure height. Weight is the determining factor, but this is weight, but I all subsea installation operation. Specify be dynamic positioning we have a minimum working depth of the vessel, which will determine the vessel depth and the minimum ROV working depth. ROV work less than say 10 meters of water. So we need to make sure that it's very clear operator that what is the minimum working depth they're willing to move. And you will also have personnel on board communication. Sometimes pre-commissioning operation requires quite a lot of more on board. Let's say 100 have been available on the vessel for the project to be so this reflected and make sure that all the vessels are and it's sometimes it's an alternative process. Vessel and then all the time to have the idea that they will adjust one now having so again structure design need to provide the so that whatever structure that they design can be installed and can be easily, safely installed. So all the marine installation is required, such as ROV docking beam, ROV trunnion, needs to be there. And we need to also perform an ROV access study to ensure that the ROV does be able to access all the passing. We also need to ensure the key passing attachment points are already incorporated in design for the transformation. So when we see vessel specification, what do we see? We see what the capacity, what's the crane capacity, what's the deck size, what the other capability it has, what its dynamic positioning. So that's what we do when we do compatibility and vessel selection and design. And then also perform the deck layout. And we're optimizing space. We don't want to do too many trips to the backyard and pick up the structure. We want to optimize it. But each trip can be 1 day of vessel time, which can be a lot. And the next one is we perform the plan. We will need to make sure that yes, the crane does have enough capacity and have enough hook height at the required radius to perform the lift loading. We also perform rigging analysis. We design the lift rigging to ensure that it's optimized for the lift and for the installation method. The input to the design is the structure weight, what dynamic method, what is the method available in the deck. You would want to make the rigging as long as possible so that it can reach the deck so that the rigger can easily access it, but not too long so that it is exceeding the available kind of crane. So this is the code that we use the NVIDIA DMO. The next, you can see there are a lot of things on board a vessel deck, and we need to make sure that they are safely secured during transportation. A vessel can roll up to 15 to 20 degrees during transportation, depending on the size of the vessel. So we need to make sure that they are secured. We input the structure weight, size, height of UT, and then we design it, we use two factors. So we want to optimize the sea fastening so it minimizes the time required to remove the sea fastening offshore. And also make sure that we minimize walking at height to avoid people climbing ladders and then walking at height. So we use the FDNO. As an input to that sea fastening design, also perform a vessel motion analysis, which it will provide what is the role of the vessel, maximum role of the vessel occurred for a certain wave height and the unit. Will then result will then feed into the department design. The input for that analysis specialized plans, the design of the vessel, the stability plan and the environmental criteria. The analysis is performed using the MOSES, multi-operational component model software. So this is the output of the vessel motion, provides the acceleration, full pitch and accelerations for the heat. We'll then also do for installation analysis. This shows the vessel and this shows the structure being lifted, going through the flat load. So it's a dynamic analysis, and it gives us what is the value of the actual dynamic load, which can be up to 2 times the static load, weight in air. And it also gives what the optimal vessel heading, and it gives what the wave height maximum that we can perform this lift. To ensure that we will have a safe lift within the capacity of the vessel and the capacity of the vessel. The analysis is performed using OrcaPlex, a dynamic analysis. Now, moving on to the conventional structure. So, conventional structure are like jackets and topsides. One of them is this Sutubang topside. So we've got jackets, stop dash, and the weight is quite a bit, 15,000 baht. So the jackets below, on top of the seabed below stop dash. What are the activities involved in installing jackets? There are the flow downs, large ballast arrangement, and check for the jacket integrity during loadouts. Jacket transportation, so you need to perform jacket and barge transportation analysis. Jacket launch, then you need to check jacket integrity during launch. Jacket upending, jacket set down, while upending, while diving. All this will require analysis that I will go through quickly later. So this is equal to for jackets. You have your loadout, you have your tow from machine located with it. Straighten the lift, and then you do the lift, lower down, and prepare to open. So jacket load down. So jacket, when they are loaded down, phase by phase, you need to ensure that the parts are ballasted so that it's level. If it's not level, then what will happen is you will induce stress on the jacket, and then the jacket may not be okay. To the ballasting arrangement to make sure that it pumps enough water so that the barge keep level. Because the load onto the barge is different than the full jacket load. So we need to perform that. And so if you can see, there are caps also that does not have support. The COD of the jacket also shift slowly floats. We need to ensure that the when you see we need to avoid this new support and ensure that it's level so the jacket is fully supported that is during the loadout. And then after the loadout, jacket will be transported to site. We need to ensure that the jacket will stay on the barge, and these barge they roll. To ensure that the roll, the T-passing design is strong enough for the roll, the barge. And then some jacket needs to be launched. A launch jacket means that the barge will be ballasted so that it's turn heavy, and then push so that it slowly roll and then go down. And need to perform ballasting configuration, and we need to also check for the stress induced to the jacket during launching. During launching, the jacket will be supported both by buoyancy and by the rocking arm, rocker beam. And that will be checked for the integrity of the jacket. The record order will perform the jacket frame analysis similar to self-structure analysis required to design rigging to optimize rigging. With the structural engineer, we also check for the integrity of the jacket itself. Is it strong enough for the lift? If it's not strong enough, we need to increase the lifting points. Then, once the jacket is launched, it will be floating, and then we will hook up the frame to the jacket and lift it, and then append it and lower it down to the seabed. So appending also will be checked for the ballasting. When during appending, the jackets are flooded at the bottom of its compartment so that it's bottom heavy, and while still leaving a bit of a flotation at the bottom so that it can right. We also is it stable on the seabed? Seabed are hard, as you know, it's soft. So at the bottom of the jacket, we have mud mat to ensure that it can stay upright. Sometimes it doesn't. So we need to make sure during the process of pile installation, whereby we will be putting or stabbing pile at the corner of the jackets, whereby there is an additional load to the one corner of the jacket, where the jacket will be able to take the load of the pile. So there is jacket on the bottom of the thing. Then we will perform a pile installation. So the jacket is basically a template for which we step the pile into the jacket, and the pile will go through and step down into the soil, which then checks to transfer the load of the outcome to the soil. The pile will also need to be designed, because we usually transport pile horizontally. We need to append it at its end. We need to make sure that the pile is short enough not to break when we lift the pile. And then we pick up usually with an ILT, hooked up to the crane, and then step to the jacket, and we'll deploy hammer on top of the pile to driving. Driving also requires analysis about pile drivability analysis. This analysis will tell you how many uh, meter that the pile will go down on the flow, how many flows per meter it will require. It will also tell you what is the spoil resistance during driving and what the point where you will say it's already meeting its capacity. When we design this, we want to avoid what you call a pile refusal, where either soil is too strong, too stiff, too strong for your pile, or for your hammer, or your hammer does not have enough capacity to grab the pile. So we would like to avoid that. We do have means to rectify that, but this is what the pile analysis will do to ensure that you can drive the pile up to its target penetration without needing to do any connectivity work. And then once the second pile is installed, then you install the topside model mooring tower. So sometimes you will have the transition piece on the top onto the jacket, and then you will have the support frame, and then you will have the topside itself installed. The engineering involved will be the topside sea fastening design, support frame design, white motion analysis, flow mooring design. So in conclusion, every project is different, and we need to achieve a creative solution. So what's important is we do this analysis so that we obtain cost solution, and that the operation is safe, so we can go back home to our loved one. So I hope this presentation is useful for your future career. The knowledge that we learned today is just a drop in the ocean. So there are still things that I haven't gone too much deeper, but if you got any question, just feel free to ask. I guess now is the question and answer. Yeah. Or should I pass the floor back to you? Okay, sorry.
Okay, thank you, Dasik, for very good and informative talk. Because I think most of us don't have this experience with the subsea, so it's refreshing. So, do you have any questions from the audience online before we proceed with the questions with the audience we have in this physical? Okay. Is there anyone from online? Okay, then we proceed to the physical. Are there any questions from the? Okay. We go with Miss Shida first.
All right, so the first question is, what are the aspects that need to be considered during subsea installation? Is it the environmental aspect or overpressure or other factors? So so basically mainly for subsea installation, there are parts that are similar to conventional structure. It's the environmental, what is the wave height, and what is the wind speed, what is the current speed, So there are limitations. Wave height limits the dynamics. The wave height affects the dynamics. The higher the wave, the higher the dynamic will be, the bigger the dynamic load will be. I will get to the second question, which asks what's the difference between a static load and dynamic load. So that wave height determines the dynamic load. The second is the wind speed. Wind speed determines the maximum speed that the crane can operate. So once it exceeds a certain speed, different crane have different maximum wind speed. The crane can't be operated. And the next one is the current speed. ROV need to be deployed. An ROV thrust that only have that much capacity to take current until it can work anymore. So subsea. Then those are the factors similar to conventional structure installation. Another factor very specific for subsea installation is the water depth. So when you design a structure for subsea installation, you need to make sure that it's designed for what is the water depth it needs to be installed. As you know, the deeper you are, the bigger the atmospheric pressure applied onto the structure. If you don't design the structure to withstand the capacity, or if your ROV are not designed to withstand the capacity of the water depth, then your structure will collapse under the subsea pressure. Will that answer the question? Okay. So the second question was the difference between the static load and dynamic load. So static load is weight in air, just your weight, like this. Imagine if you jump, there's a bridge, a wooden bridge, you just go there slowly. Maybe the bridge will be okay. Imagine if you jump higher, your load applied to that bridge is called dynamic. The higher you jump, the higher the load will be applied to the bridge. So there is different static and dynamic. Static is basically what you weigh. Dynamic is what you weigh when you jump. So taking that piece to the offshore is when we deploy load and overboard, the crane is usually overboard with to the starboard or the port side of the vessel. And it's got a moment, overturning moment. So each move is amplified by the overturning moment. So then the structure, instead of lowering slowly, it also jumps like we jump. So there's dynamics there. So we need to make sure that the waves are low enough so that we can install it with as little dynamics as possible. Usually we can do that by turning the vessel into the wave to avoid too much roll down. Will that answer the question? All right.
Next question from Yusuf.
there's error. Oh yeah, okay, got it. Okay, okay, okay. All right, okay. I think there are a few questions there. I'll try to remember them all. The first question is during the suction, how are the vessel or person on board monitor the lowering and make sure that it's correct? Okay, let me go back to the previous slide. Okay, so during the lowering of the during the lowering of the foundation, the ROP will be docked into the hydroduction plate located on top of the foundation, and it will provide a position, and that position can be seen by the people on board the vessel. So there's a survey screen which you'll see later in the video that determines what is the position of the foundation. And on top of the pile, there's also something called bullseye, which provides inclination of the foundation. And then when we push the pile onto the cement, the ROV that docked onto the pile will observe that bullseye. The ROV has a camera, which is also connected to the surface, and we can see what is the inclination. So from that, both the crane and the ROV work together to make sure that the position of the pile and the inclination of the pile are held in the correct positions. So that is how the people on the surface monitor the correctness of the position. During lowering of the pile, also the second ROV has a camera that also can be seen from the people on the vessel, and it can tell you whether what's the penetration that the pile has reached. At the side of the pile, there are penetration marking that indicates how far has the pile penetrates. So that gives you indication on whether you've reached the target penetration, whether you've reached the self penetration required or not. What's the speed of lowering during vacuuming that is allowed. So that answer your first question. Okay. But second question is, I think, oh yeah, why vacuum? Does that introduce weightlessness? It doesn't. Actually, it's like when you a straw, that creates a vacuum inside the straw, which will allow the fluid to go up. So the fluid inside the foundation, or the soil inside the foundation, is actually not pure soil. It's also fluid. So these are also mud, and at the top, they are still part of the foundation. that is on top of the seabed, and they are still fluid inside the cavity of the foundation. So the suction takes out that fluid and create a vacuum that allows the external subsea pressure to push the foundation down. The principle is the same like when you cut your straw. It pushes the foundation down because of that the difference in pressure between the inside and the outside. So does that answer your question? All right. The third question was, will you introduce error to us? So geotechnical and geophysical, I think is different. So when we perform these installation, before we perform this installation, we perform a soil sampling. We drop a geophysical core and sample the soil from the seabed up to whatever we need to the foundation to penetrate. Usually up to 12 meter or 15 meter only. What you guys do is much bigger than that, yeah?
Okay, horizon to horizon.
Yes. Seabed survey also. Uh, but what is important is what is the soil capacity? What is the soil stratigraphy between zero penetration to, let's say, the bio depth is 50 meter or 0 to 15 meters. And then you will, based on that core sampling, you can see what's the layer of clay, mud, or hard soil. You can see that. And our geotechnical analysis engineer, actually one of them is Sandy, I was online right now. We perform that analysis and determine whether you can actually install the pile or not. Now with soil, they are not as predictable as on-surface material like steel or wood. You know, steel has the yield capacity of something. But the thing is with soil, there's no certainty. So they will have a lower bound and they will have an upper bound capacity, in which that lower bound and upper bound means that you will have a lower bound capacity on what is the self penetration. If it's lower bound, it means that you are underestimating the soil capacity. If it's upper bound, capacity, and so you can have a penetration that's so little. Oh, self penetration will be between 4 to 6 meters. 4 will be the upper bound, 6 will be the lower bound. Do I get that right? So, yes, there are errors possible, even with the lower bound and upper bound. But we do it conservatively, and even they have designed, when you design a structure onshore, you design with a safety factor of, for example, overcapacity, for example, a safety factor of 2. But soil, when you design a foundation, the safety factor is not just 2, I think it's 4 or 5, because we don't wanna overestimate the capacity of so to avoid that over design within the parameter of the code given to us. So yes, error will be there. Our design we over design it so that the error won't be detrimental to the capacity of the truck. That answer your question.
So the safety to be checked.
Oh yeah, okay, correct. So the last question was, what happened if the structure or sinks? So we had cases before where we didn't expect the structure to sink. We overestimate the or soil capacity. The ROV can be equipped with a ROV suction dredger. So basically, it's another pump that sucks, but it's mounted to the ROV. It's like a vacuum cleaner. So the ROV is mounted with a vacuum cleaner, and it vacuums the fluid and soil located around the sink structure and recovery, and allows us to put an attachment point recovery. Uh, for those cases, it very rarely happens. For those cases, we usually very conservatively put a huge metric or mud mat on those type of structures. It's very rare that that happens. It's very rare that it sinks because when we design it. Um, but what sometimes happen is, let's say, pipeline lay down head, which was supposed to not sink on seabed but sink. Those pipeline lay down heads, just a small pipeline lay down head. It doesn't have mud mat, and we don't feel the need to, but it sinks still strong because seabed was so soft. So that happens. So when that does, put the vacuum cleaner on the ROV and suck the area around it, pipeline lay down head, and then we recover it. That answer your question.
The question is still, but I'll give it to Walkies first to address it.
Figuring that guys are geophysicists, so a lot of questions about soil, but that's understandable. So as a civil engineer, we also do soil sampling, rock boring, drilling, both onshore, and we also do the same uh, offshore, subsea. We will have survey vessels, we subcontract them, and go out and then perform uh, the geocore sampling. So either using rock core to check what the seabed soil looks like, or even drilling and to obtain these geocore sampling up to that, let's say that 15 meter. So yes, we do perform that. We also perform this using sub-bottom profiling. Let's say we want to do pipe laying. We perform two kinds of survey. Using the multi-beam echo sounder, we perform seabed survey. With that seabed survey, we'll be able to see how the seabed looks like. Whether there's a valley, whether there's a sudden drop, incline, so that we can plan where we want to put the structure. We would avoid putting the structure at a location where it is too inclined, let's say more than 50 inclination. We want to put the structure at where it is level. And we would also want to put the structure, and sometimes there's a underwater river that occurs, and we would want to avoid putting our structures at that underwater river. So that multi-beam echo sounder survey will provide those information to us, which will be an input in the engineering design. And the drop core sampling will provide the soil strata, which will give the technical engineering input when they design the subject capacity. That answer your first question. The second question is about difficulty when installing offshore. Oh, every time it's difficult. There will always be challenge. Equipment doesn't always work. Vessel doesn't always work. Rain doesn't always work. ROV doesn't always work. Wet weather, yeah, wet weather, weather forecast, we can see whether it will, what's the weather forecast will be. Sometimes it's not right. Current doesn't always work. Local people doesn't always be cooperative. Fishermen is not always cooperative. Things got lost. Someone forget to bring things. A lot of problem happens, but that's our job. That's what we do to solve those problems. What we need to remember is that not that we don't consider it as a problem, we consider it as challenges. But yeah, it's quite a challenging place to be working in, especially because offshore. Say you say you go backpacking and going to let's say Johor or Singapore, you sort of bring things. And if you forgot things, you can just buy at the closest minimarket. I got for the convenience store. But offshore, you've got to bring things. This bar, and then sometimes the items that we forget is long. So yes, challenging, and we need to be on the ball, making sure that everything are planned correctly, making sure that it's very detailed plan of the operations offshore. Yes, detail what happens step by step, what materials are required, task plans are prepared to make sure that every step of the way we avoid unnecessary problems. Things that we can control, we control. Things that we cannot control, we solve. Great people there, offshore. Great, great people who can work under pressure while still being cheerful and cooperative to their team members. I haven't even talked about the vessel, I haven't talked about the ROV, I haven't talked about the people, I haven't talked about engineers. A lot of things that I haven't talked about, but there are problems, but we will get on it. That's the answer to your question.
Nothing to do inside. Okay, my question is actually my husband he work in the subsea. Okay, but anyway my question is like all I see here all machine, all ROV. Do you have divers to help help only everything is all machine based or ROV? Because actually the diver will do all the soldier, right? Of the structure.
So this is one of the hidden slides. Yes, there are divers supporting the operation, but as I was just talking about installation method and engineering, I haven't touched about the vessel the equipment required, so that's why I didn't touch it. But there's a question on it. So yes. Diving. Um, for shallow water installation like jacket, yes, we will employ diving. The operation involving diving, for example, tie-ins for installation, subsea, cutting of routing line or removal of lifting points. But yes, there are divers, but divers they will go for 180 meters. So subsea operation and lock operation up to 1,400 meters. So even uh, so RV also a very crucial part of the operation. Sometimes we have two ROVs. So, so for subsea operation, we don't usually have divers, but for jacket installation operation, offset operation, yes, we will have divers. So there's a totally different spread between the conventional offshore mobilization and subsea offshore mobilization. Yeah, will that answer your question? All right, the first question is how to determine the installation location. All right, when you say how to determine the installation location, when you say about location, you mean the wellhead location? Okay. Uh, well, um, when you model your reservoir, you would know where is the reservoir is located. You would know where is the cap that traps oil and gas. So that cap, you look from the top view, you'll be able to see where's the cap. You'll be able to see where you want to drill, correct? But then you also have the ability to also perform horizontal drilling. So you're not always limited to vertical drilling where you need to always have your wellhead right on top of the cap. And then you will have several spots where you want to drill, correct? And even when you have a wellhead, you can perform directional drilling from one head to a lot of caps, right? And from there, you determine where you want your wellhead to be. How many wellhead, how long you want to do the horizontal drilling, based upon the reservoir available. And from there, you will determine where you want to put your manifold. Let's say you have the Christmas tree. You are thinking that, yes, I don't need a manifold, I can just go directly to a vehicle. No, for this one, no, I need a manifold. There's a lot of production involved. So where do I want to put the manifold? There's an field of knowledge called subsea architecture design. Okay. So that's one semester in NUS, where you determine where you want to put your wellhead, where you want to put your manifolds, where you want to put your FPSO. Mm, taking for example like this, where do you want to put your FPSO? You put it, let's say, where do you, let's say at a shallow location. Where do you want to put your CPP also at a shallow location? Why do you want to put your FPSO there? Where you would want to put it shallow so it doesn't, you don't have to have an anchor that's too deep. Where do you want to put your FPSO? You would want to put it right in the center of your field so that you don't have pipeline too long pipeline. Then your pipeline and pipe cost will be too expensive. Where do you want to put your tree? Whether you want to direct vertical or horizontal drilling, where you want to put your manifold. Manifold, what you would want to center around, you would want to center the manifold around a lot of your trees. So it's going to go to its length. So again, a lot of that is actually decided during the pre-feed, during during this stage. There's a simulation we did, which I'm not very familiar. Mm, interesting. I thought it's you who decide. Interesting. I've not been that fortunate to be involved with operator, but my understanding is there will be a pre discussion between both BCI company and the operator and discuss it. Who they will propose. They will tell us, you get with you will tell us where the reservoir located, and then we'll suggest how the subsea architecture will be. So let's say the government offers a solution. Let's say technique offers a solution, and then you will assess and evaluate how much both solution cost in a tender study, and you will select which one of this is actually cheaper or more beneficial for you. Some company may offer you just a few wellhead, like a lot of drilling. Some companies may offer you a lot of wellhead, but you don't have to do horizontal drilling, so it's cheaper. Overall cost, you need to compare which one is cheaper. So I guess it's determined by both you and the PCI company, the operator and the PCI company. Will that answer your question? The first one. All right. The second one, I think you're asking about duration until it's finished production. Okay. It depends. Some facilities are simple. Some fields are small. Only have one Christmas tree, one processing platform, and that's it. Installing a jacket will only take 1 month, and then you can start operating. But fabricating the jacket takes 1 year. Fabricating the CPP topside takes 2 years. So buying the valve, the piping, the control system on the top side, for the SP, for the subsea structure, that can take 1 year, 1.5 years. So you are looking at around 3-4 years BPCI, or I forgot, engineering. That can be half a year, 1 year. So it depends again on the complexity of the project. There are projects where you between the tendering and the installation and operation, maybe just 1.5 years. There are projects like that because the operator has already engaged another subcon, procure and engineer the material. All we need to do is just install them. But there are projects that are complex, that span 6-7 years PPI. So again, it depends on the complexity of the projects. Will that answer your question? All right. Correct. All right, equipment rental or vessel. Correct. Yeah. So there is another aspect of the operated called the vessel and supporting vessel planning. So when we perform installation operation, we sometimes need another vessel and a rig move, for example. To perform a drilling operation, you would want to charter a drilling rig. So these drilling rigs would rent. So that is, yes, if the drilling rig is a DP drilling rig, you would consider it as subsea operator. That answer your question? Yes. Yes. Oh. Go ahead. Yeah. Sorry, I didn't catch. Was there any what clashes or differences? All right. Yes, there's a lot of differences. I started my career in civil engineer doing the conventional structure. So the the spread that would be more, we could use what you call an anchored barge when you do a biplane. You do anchored barge where the barge will have anchors or 12 anchors, and they would throw that anchor, will have the HD move forward, put their anchors, the barge will move slowly when they do biplane. But for subsea operation, obviously you can't drop anchors. So what we do is we'll have our vessel called 105. They'll spool up the pipe, rigid pipe, and pull it up, store it on board the vessel, and then lay it onto the seabed without any anchors. Just dynamic positioning. Just roll slowly on the seabed. Like I earlier said, when you do subsea operation, you want to do intervention, you can use diver if you're on shallow water. But you can't do that for subsea operation because you need to have an ROV for performing subsea operation. And for structure, conventional structure located in shallow water like jacket and topside, you want to go there to the jacket and fix something up, you can go there yourself. But the subsea structure, no, need your ROV to do it. Whatever intervention, releasing shackles, then they need to be done by the So those are the different conventional and sea structure. Will that answer your question? Yeah. I think it's a good time to ask. But you know, the why there was the ring. Thinking, so what would that put wrong? I think from your where the what I don't think the year before in 2022, pressure crash to the oil platform. This was the Sarawak. So the problem is you saying that the table extra grow because of the bad weather. Because the bad weather was as president. Is that something wrong? What could have gone wrong? Whether the visibility analysis and the mixer cable, getting something properly or what? Okay. All right. Welcome. That's another company's vessel. I'm not fully familiar with what has gone wrong or what's the result of the investigation, but I can give you a brief explanation on anchor operation and dynamic positioning operation and why it can fail. So when you moor the barge or a barge or a moored-based drilling rig, the anchor itself, we've got a lot of redundancy. You only need 8 anchors, but you deploy 12 anchors. But sometimes there are things that happen. The weather went up above the capacity of the anchor. We didn't deploy enough anchors in time during bad weather. They thought that it's not going to be the bad weather because the weather forecast didn't think that, so they're not prepared. The anchor itself could be insufficient because soil is not optimum. The wire rope itself can be broken because of the maintenance or because there's not enough tensioning. When we do anchoring operation, there will be anchor operators on board the vessel that tensions all the anchor wire at the same time to ensure that they are all uniformly tensioned. Sometimes maybe they didn't do the tensioning properly. So those are the factors that can affect failure during anchoring operation. As for dynamic positioning failure of vessel crash onto a platform, that's why we have DP2 and DP3. DP2 has one redundancy, DP3 has 3 redundancy. At a very, very rare case, if let's say one dynamic positioning system that consists of a full separated system of VC, sensor, which navigation satellite, which the position of the vessel fails, there will be one as a backup. But at a very, very rare case, both of them can go down at the same time. And there may be also a sunspot, they call it a phenomenon, which will create errors on the GPS of the vessel. That can also create failure in the dynamic positioning operation of the vessel. That is why when the vessel is operated close to the platform, they will also put another survey system. They will have a marker placed on the platform, and the vessel will observe the distance between the vessel and the platform to avoid those things from happening. But yes, a lot of factors can go wrong. Redundancies are placed, but there glitches happen. So that may be the case of such redundancy. Does that answer your question? Correct.
We have now reached the end of the session. Thank you very much, Mr. Asit, for the very interesting talk on the subsea offshore structure installation, for sharing your knowledge, taking all our many questions. And then we also share I give another view on the industry, because for us, maybe for geophysicists and geologists, we only see the soil, we see the reservoir. But now it differs different, like the offshore, like like in the oil and gas industry, it's not just us. We have the upstream, like exploration, production, and we have to work together to get a successful like oil and gas. So I hope everyone received some important input from this talk and knowledge. So congratulations for everyone for attending the talk, offline and online. So I hope this first 1.5 session is very beneficial. So before ending today's session, we would like to ask everyone to switch on your cameras for a photo session with Mr. IR Asit. Okay, so yeah.